Start recording. Okay, let's minimize OBS. And so, last time we forgot to do one little thing, and it's just a little thing. So if we just run our little program here, and that was, we tested like, can we separate that way, and can we separate that way, and this way, hit the right button, and so on. One thing we didn't test was, if we stick a square right in the middle, do we separate? And the answer to that is yes. So that was just one thing we neglected to point out, and also the other way, if we have the second one is the outside one, it still works. And it's symmetrical, so it doesn't matter what order you put the boxes in. So that was just worth testing. And you recall that makes sense, because the way we do our separation is like, if we have two shapes, we're basically moving the start of one to the end of the other, or we're moving, the start of one to the end of the other. So either that one's going to end up here, or the small one's going to end up here. And this makes sense, even if there's one inside, we're moving, the start of this one to the end of that one. So it's always going to end up outside. And similarly, the other way, moving the start of this one to the, the start of this one to the end of this one. It's always going to end up outside. So that all makes a lot of sense. So that was just worth pointing out, because you'll recall we had to think about that with the circle one as well. And as we determined, it was the same process, the same algorithm. So that was a little review of what we did last time. So let's have a little look at what we've basically been doing. Can I scroll? There we go. That was a little look at what we did. So what we've done this in like two parts. We've got, we did circle versus circle, and we got those working. And we have rectangle, axis aligned rectangle versus axis aligned rectangle. And so when we did the circles, we figured out a bunch of stuff about basis vectors. It's like, we can subtract these two and normalize it, and oh look, we've got this axis that points in that direction, and it points in that direction everywhere, but we figured that out. And then if we take the perpendicular, we can go up a bit, and so we drew our nice things on either side of the line and so on. But we kind of fudged the projection bit here. So when we projected these onto this line, we didn't so much do a projection as we sort of, I guess we shortcutted the maths, and we just said, well, this is here at 0, and this is at whatever length away, it's like that. We figured out length just by, it's that far away from this point. And so then we just subtracted out the thing. So it's like it goes from there to there, and the red one goes from there to there. And so we just stuck the radius in. So we kind of fudged the projection there. And then this one, let's see, what do? We also kind of fudged the projection, because it's like, well, it's axis aligned. So we've got an x-axis, we've got a y-axis and an x-axis. And this one is, goes from there to there, and this one goes from there to there. And we just use the x value and the y value. So, y value here and the x value there. But what we did, we figured out two things in this one, and that is, first of all, we need to test multiple axes. So this is like, we need to do the x-axis and the y-axis, and we need to test them in multiple ways. And the second thing we figured out was, these could be in any order. Unlike this one, where it's always, the distance away is always positive. So the way we fudged it, we could just rely on that fact. In this one, we don't know whether this one is positive or negative on the x-axis in relation to the other one. So we had to be able to handle these things being in either order. And now we have a little smiley face. Okay, so that's probably the important points for doing projection, and that is, we need multiple axes and we need to handle them in any order. The last piece of the puzzle is what we're going to do today, and that is we're actually going to stop fudging the projection. We're going to actually do the projection properly. And the reason is that we no longer have this, this sort of fake distance business, and we no longer have these fixed axis aligned things, because what we're going to do is we're going to do rectangle versus circle, and we'll probably only get part of the way through this, but we'll come back to this maybe next time to actually do the separation. But we're going to get the maths and the projection stuff down today. So, when we've got a circle like this, we can just work on the x-axis. That's pretty simple. It's like this goes from there to there. That's fairly straightforward, and we can just take the x position and add and subtract the radius. Sort of similar to what we were doing here. That's pretty obvious what we're doing. And of course, the shortest distance to get this circle to separate is out there. So that's fine. And you can imagine we can slide this circle up and down, and it's always going to separate this way out. And you can imagine if you rotate this 90 degrees, you get the same effect. If the circle was up here and we were sliding it along, it's always going to separate out that way. Where this changes is if the circle's up in the corner. So if we're up here, and hopefully what you can see is now, it's this far to separate out that way, and it's this far to separate out that way, but it's actually only this far to separate out of the corner. So, and this is where this axis comes in. So we have the center of the circle, and we're going, and I'm just going to tell you how this works, and that is, we test circle versus the corners of the shape. So we've got basically when you have a circle, how do I describe this? So when we have squares, we have these two axes. No, that's not a good word. Let's say we have a square and a triangle. I think I've drawn this diagram before. And so when you have a square, you've got an x-axis and a y-axis, say the axis aligned. When you have a triangle, you've got an axis here and an axis here and an axis here. So we have to test all 5 axes. So we've got 2 coming from the square and 2 coming from the triangle. So in the case of the circle, it's a bit of a special case. We've got 2 coming from the square still. We've got the x and the y. But the circle, we have circle to all of the points, because you can imagine that if it's rubbing up against an edge, it's going to use one of these ones. But if it's rubbing up against a corner, neither of them apply. So what we have to do is take the circle and then test it versus all of the corners. Now we could do some funky things to say, well, it's nowhere near this corner, so we can just skip testing this axis. But that's kind of an optimization, because as we know, the way the separating axis theorem works is, we actually theoretically test every single axis and see if any of them have this gap here. And if any of them have this gap, they don't intersect. So if we test an XS axis and it's it doesn't add any information, we're not really losing anything. Does that make sense?
Yep.
Cool. So what we need to do now, so now we have we kind of already know how to do this. We'll do this properly as well, just to make the maths the same. So we already sort of know, it's right, we've got an axis, we just subtract the radius and add the radius to get the circle onto it. But if we have this rectangle, and we've got a circle up here and whatever, and we've got this axis running through it, we need to be able to project this rectangle onto this axis and be well, it takes up that section there. So does that scratchy looking diagram make sense that I just drew there?
I mean, yeah. I mean, I don't know how we're gonna do it, but I can. Yeah, I mean,
Yep.
it's the corner axis. It's not the edge. Like it's not on the sides, and in order to get that, you have to drag it across both corners, I guess, that intersect there.
So I'll draw that diagram a little more neatly, because then it might give you a better idea of where we're going with this. So if we've got a rectangle, and I'm not going to draw the circle, I'm just going to draw some arbitrary axis, like, let's say this one. And what we can do is we can say, well, that point goes to here, and this point goes to here, and this point goes to here, and this point goes to here. And despite my poor drawing, they're all 90 degrees. And so what we can say is, okay, if we take a min and a max on this axis, we can determine the sort of area, well, the span. Is it a span? I'm not sure the correct mathematical term for this. On this axis that this rectangle covers. So that might make a little more sense. Yep.
Yeah, it does.
So,
I wonder if this is how the those Fruit Ninja games kind of figure out where to slice off a piece.
Well, the maths is actually probably a little bit similar, but I was actually just going to get into a thing that sort of demonstrates why that's not the case. So let me show you this. So if we have, we've got these lines coming out intersecting this green thing at 90 degrees, what would happen, for example, if we did, this and extended them even further, and we drew another axis here? What happens is we actually get the same result. And this tells us something interesting about the green line. So what this says is that the position, that way and that way of the green line doesn't matter, which kind of, in a sense, tells us that the green line is only a direction. Does that make sense?
Not at all. The part where it doesn't matter makes sense because it doesn't matter where you put it. You're still gonna always project the bits down onto it, and it won't change. But not the part where you say it's just a direction.
Okay. So, yep. All right. Well, let me now add something to this diagram. What I'm going to add is an origin. So if this is the origin, what we can say is that let's see, if these are just out in space like this, what we can say is let's draw the green line through the origin. So it no longer has, like, it's got a position of 0. And and we get obviously the same result again. And so what we can say about the green line is it only matters what direction it's going in, because also obviously this green line goes on forever, and forever in this direction as well, because we could imagine we've got more shapes out in the yonder, and we're projecting them onto it as well, and they project it.
Sure, but when you say it's a direction, I mean, then you said it could go either direction.
Yeah, so this is like positive and this is negative. So you could represent this as basically a, this is I'm going to call it a hat for axis. I heard a thinking noise.
No, sorry, did you get cut off? Because
No, I thought you were giving that some thought. What do you think?
no, I'm not giving I'm not giving it any thought. I thought you were done. You said a hat was the axis.
So we're going to call a hat the axis, and what we know is it's a direction because it's any length, so it may as well be length 1. And it can go in either direction. Yeah, So, this is just negative a hat times something, for example, or just this is just a hat times something. So that's another way to look at it. Say we want like the orange point. This point is like q times a hat, and this other orange point might be r times a hat, and this is like f times a hat, and so on. It's like we can get any point along this line by multiplying a scalar by this unit vector.
That makes sense.
Yeah. So, and that's where these points come in. They're just some scalar times this unit vector, and so once we've done the projection, we no longer care about the actual thing. We just care about the scalar, and that is how far along this axis are we. And so that's sort of the result of the projection. Make sense?
Enough.
All right, good. I'm glad
hanging on.
Sorry?
I said I'm just hanging on by a thread from not totally awake.
That's all right.
I get what you're saying.
Okay, so then the final piece of this puzzle is, all right, this is the problem we're trying to solve. We've got an axis, and it can be anywhere. It doesn't matter where it is, sort of in this direction. It's just, okay, it's important that it points in this direction. So we may as well, if we need to conceptualize it, we'll conceptualize it around the origin. The last piece of the puzzle is, okay, we want this point, and we have this point. So what we're going to do is an operation that looks like this. So we've got, this is the corner of the square, and it's like, we'll call it M for fun. And we want to project it down onto this axis for which we have this unit vector. So we're going to call this operation project onto a hat M equals there. And what that's going to give us is, let's call it N. Let's call it N. So N is going to be, just like we had this scalar times this thing, N is going to be the distance along that. So that's going to give us N. So this is the operation we want to do. Does that sort of make sense from a...
Yeah, I mean, you're gonna I know where I can see where M is, and the green line is a hat. So if you project M onto a hat, you'll find N, which is what you want on the line.
Yep. Okay. And then so
yeah, you'll do that for all the points, and then you have something in a uniform space that you can do your separation on, because now you've got all the points in the right spot.
Exactly. So, let me see. Okay, so this is, for those of you watching on YouTube, if you have seen episode 5, we basically went through and we figured out what this was back when we were doing sort of purely whiteboard stuff. So just to like run through this at super speed, we want a thing where we've got, a direction, and we want to project down onto this. So if we were to say try to build this operation up, one thing we could say is like, what have we got that looks like this? For example, we're trying to project at 90 degrees onto a thing. One of the things we have for that is a circle. And if we've done some trigonometry, which we've done, we know that if we have this vector here, we project down onto the x-axis at 90 degrees, we get cosine theta, where theta is that angle there. And this should look sort of vaguely familiar, Daniel. Yes?
Yep.
So what we know, so say this is, if this is B, then say this is like B hat. We'll get, the cosine of B hat will be here. So, and this would be, so what we're doing is we're just rotating everything around so that, it all comes down, and we're pretending that this is the x-axis, but it's, actually, A hat down here. So that's sort of, because we're working from this angle theta, we only care about the relative angle between, a hat and b hat. So we just rotate the whole thing around and be like this. This is a hat for fun, which for this purpose is like the x-axis. So you can kind of fudge through that rotation. Does that make sense? Just, we only care about. Sorry.
No, that doesn't make any sense at all to me.
Okay, so
sorry.
So basically, what we're saying is we only care about the angle between these 2 points. We don't care about which direction they're facing at the moment, just for this particular operation.
Right.
You can imagine.
So the dash line is cosine theta, and theta is that angle. But then you said that b hat. Go ahead.
I was going to say that this distance here, that distance is cosine theta.
Right. Oh, okay. Sorry. And the dash line is the perp of b hat.
Well, the dash line we're not really going to use. We just draw that to indicate that this is a 90-degree projection down onto this axis. But if you wanted to say the distance of the dash line, that's sine theta.
Okay. Oh. Okay. Yeah. Okay. Cosine theta, sine theta, and.
So.
But why do you care about getting the relative angle between b hat and a hat?
So that's just so we can make this operation work. So the same operation works here. If we call this b hat, and we go down there at 90 degrees, this is going to be the same distance from there to there. So if I draw in like the unit circle, it goes there. So it's the same. This is the same diagram. It's just rotated. And so this distance, this orange distance here, is still cosine theta.
I get it. Okay.
Cool. So what we can do now is we can extend this literally. So we've got b hat. I'll do it on this diagram. And we want b. So we just make that grow. And we make that grow. We make this grow. And then all of a sudden we have... and so what we've done is b equals the length of... the length of b times b hat, which means that this, because if we scale triangles, all of their sides scale at the same rate. This green distance here, that is the length of b, because we've multiplied this whole triangle by the length of b times cosine theta. Does that make sense?
Yeah. So we know what b hat is, and we're just scaling it by the length of b to get b. But like, how do you scale by the length of b to get itself? Like, you're looking for b, you're scaling it b hat by something, the length of b. But
this is an equivalence. Like when we start, recall what b actually is. B is, in this diagram, is m. So this is our b, is like this point here that we're projecting onto an axis.
Yeah. So okay. So that's when we already have that.
We already have b.
The only reason you wanted to scale it on the b hat is so that because the cosine of theta will be the same length as the b, then you can get the point where it touches that spot where you want it, which is what in this diagram, this is like a hat, or the cosine a, but cosine a only goes to a. Your orange line is cosine theta, which is going to a hat, but you want to extend that to match where your b is, and you did that by scaling the length of b to cosine theta. But I don't know. I mean, I can see it on the screen, but getting the length of b The length of B, but the is basically a point. It's the
So,
length of B relative to B hat, right? I don't get it.
okay,
Sorry.
so the only reason we have b hat is because we derived b hat. So this is not an operation that we're doing, say, in code. This is just some maths that tells us that b is equal to the length of itself times the direction of itself. So it sort of says b decomposes into this. So what we could do is say algebraically that we can go to b hat equals, we shove this around the other side, b divided by the length of b. So this should be super familiar.
It's like normalization. That's just
Exactly. So you've just normalized to get b, and the only reason you've normalized to get b, normalized to get b hat, is so you can do this operation here. So you can say, well, now we have a unit length vector and a unit length vector. We can take the angle between them and get the projection of the unit length vector down onto the unit length vector.
okay. So in the original operation of projecting a hat to M, you're just getting the other side of that so that you can get M relative to a hat and get that the B length of B cosine theta is what you're looking for, right? That position.
Yes. So basically we're scaling it down so we can do this. We can say, okay, now we can use cosine theta, and then we can just scale it straight back up again.
Straight back up again. Yeah. Okay.
So that's just to let us. Yeah, it's just to let us use our unit circle trigonometry stuff.
Okay. Yeah. This is why we were supposed to review this before. But yeah, I get it. I mean,
fun.
it's sort of there. I can follow.
The nice thing about this, is once we've done it and we've coded it, we'll just write the function that's projection onto some vector, and we'll just have it, and then we'll have this video, and we won't have to worry about it again. So we're nearly done. So the last little bit of this fun thing is we know about an operation called the dot product. So when we see this, it's like, okay, we're now in a position that we have, like, okay, I've got my axis, I'll draw it out here, a hat, and I've got my vector b, and I want this business. I want the projection of onto a hat of b is this position here. So that operation, and I've got all this. The only thing I don't have is theta. Now we could get theta. We could use a tan 2 y x. If you recall, we have this operation that lets us get theta equals that, and we'll just get the relative angles of the absolute angles of a and b and subtract them to get the relative angle theta. So I won't actually put theta equals that because it's actually not theta in this diagram. So you recall we have this operation, so we could in theory do that.
Right.
But obviously, as I've said before, if that if you have a tan 2 and like cosine theta appearing in the same algorithm, you've probably got a bug, or not so much a bug, you're probably doing it wrong, because you're basically converting vectors into an angle and then back into vectors with the cosine. So we'd much rather just skip this whole thing. No one wants to do a tan 2. We want to get rid of this theta. Now fortunately, we'll substitute this in. This is b, length of b cosine theta. We know an operation that looks a lot like this, and that is the dot product. So if we have a dot b, for example, we know that, let's draw it out here, a dot b is equal to the length of a times the length of b times cosine theta. And this is just a formula that you need to remember. this should look familiar. In fact, I think we have, possibly we even have the code for this somewhere.
We've done it.
We have
I
done
recall.
it. So what you'll also recall is that we can, now we have the dot product, we can say, right, we don't want to cosine. The dot product is basically what lets us link, angles with not doing angles. Because the dot product is also equal to ax bx plus ay by. So it's just two multiplications and an addition, which, as you can imagine, is a lot faster than doing a cosine.
Right.
Yep. Okay. So all we need to do now is we have this formula. What we want so badly is to convert that into a dot b thing. So we have to basically say we've got this. How can we get it into a form that looks like this? So I think that's really easy because we know that the length of a is 1 because it's an axis. So if we define the length of a as 1, in fact, I was going to do this the algebra way. Let's do it the algebra way because that's probably more useful. So we have b. So the point that we want, we're going to call this c. Actually, yeah, we'll call it c. And that is just the length along here is going to be c. So it's the same thing as that. C equals that. So c equals b cosine theta. What we're going to do is we're going to multiply both sides by the length of a. And just like over here, where it's like, well, we didn't have this, we just used it to get the thing that we needed. We don't have the length of a. The length of a is not particularly relevant. We're just going to pretend we have it so we can do this formula. So length of a equals that times length of a, length of b, cosine theta. Now, all we need to do is, a c equals a dot b, and then c equals a dot b over the length of a. So that's slapping that across the equal sign. So all we need to do now is we can convert that to a hat dot b equals the length of c. If we
how did you do that? I mean, I thought the length of a was 1 a while ago. I thought you were just gonna throw it away.
So basically what I've done is I've introduced a length for a here. So you'll notice that in fact all throughout this maths, a hat turned into just regular old a, because basically this maths works both ways. So you can do it the other way where you just start off with, a is just, this is a hat, and this is a, and the math still works. And what
so you're just substituting a for a hat because you can, basically.
So yeah. So this is a little bit more like an operation that we do on the computer, and that is we're going to say, well, we have some vector a, we're going to turn it into a length. Into a direction, into a normal, by dividing by its length. So we've already divided by its length, so we don't need to do it again, and we just end up with this.
I see. I totally see it now. Sorry. Yeah. Again, you're just normalizing. You're just normalizing a with its length, so you're literally turning it into a hat with that division.
Exactly.
Like a is becoming a hat, and yeah.
Well, yes and no. You'll notice that this line, if we divide this, actually, does this work? I don't know. If we divide that by a, the length of a, we end up with, let's try it now. Just do some impromptu maths. Ax bx plus a y b y divided by the length of A, which is the square root of ax plus ay, so, ax squared, bx squared. Sorry, ax squared, ay squared. And you'll notice that this operation is a pain in the ass. No one wants to do that operation. But fortunately, we don't have to. This is the sort of thing that I'd have to plug into like Wolfram Alpha or something and be like, hey, what do you think, Mr. Wolfram? But whereas in this scenario, we can just say, if we define A as 1, then this goes away.
Right.
And fortunately, not only does this go away, but this, what would you say? This. I mean, this works. There's nothing really more to say about it. That works. I'm trying to think. There's another way of doing this, which is divided by the length of A. There's another way of doing this if you want to write a projection operation where you, like you can. I've seen a formula where it looks like there's a squared there or something. I can't remember it off the top of my. Oh, I know what it is. It's vector projection. So if you wanted, I think this is now just going off fuzzy memory. If you wanted C times A hat equals blah, things get a bit more interesting because what we have here, C is a scalar. So A is a vector, B is a vector, C is a scalar. And does the fact that C is a scalar make sense?
Sorry.
No, you muted.
That was muted. Yeah, I was muted. But yeah. C. Yeah, I can see that C is a scalar for sure.
So if we wanted C as if we wanted C as a vector, all we'd have to do is multiply C times A hat. So that vector here is C A hat.
Yep.
Just like we had over here, F A hat, and so on. So that's all of the maths. So all we have to do, and this is why this technique is so useful, I guess, is because this operation here is really cheap, particularly it's really cheap if you have that as a unit vector. If you have to generate that, then you have to do a square root to get the length of that to divide it to get A hat. But that's okay, because most of the time we can actually pre-generate that. So for example, stop on the other slide. If we have, for example, a square, we can just say it's that, or it's that. If we have a triangle, that's not a triangle. If we have a triangle, we can say, it's that, or it's that, or it's that, and we can pre-generate these. And if these shapes rotate, we can also rotate the direction, so we don't ever have to do a square root to get, the length. Whereas if we have a circle, we have to figure out what that is, and that's going to change as the circle moves around. So we're going to have to get a length to get, that axis. But for fixed polygons, we can actually skip the length step, and so this becomes very performant because that is fast, because it's obviously this one. So that's all of the background math. So you're happy with all of that background maths?
Oh, not at all. Quite sad about it, really. But yeah, I mean, it's all review, which means it's all grokkable at some point.
And I mean, look, this is useful to have. This is all the background stuff, but all we really care about is this projection operation and how we got there. You just need to know that this exists. You don't actually. I mean, it's useful to be able to regurgitate this stuff, but even I have to sit and think about it for a while, and I have notes to work off here. So it helps to know that this exists, but you don't have to memorize it. You don't even have to memorize that. We're now gonna implement projection onto a vector. And we'll just slap in a dot product because we know that's what we want, and we're golden. So let's go back to the code. So the way we're going to do this is we're going to do this because I think it worked really well. You recall down here we have this if circles count equals 2, and we draw this business here, and I think this is the best way to go about doing this process. So all we're going to do is let's start drawing just above here, and just to make life a little bit easier, maybe we'll turn off the circles for now. And what we want to do is, where's my painting? As we were looking at this before. I don't know what is wrong with the scrolling on this thing. As we were looking at this before, as we noted, this axis can move up and down, and the results we get here don't change. So what we're going to do is just say this axis is around the origin. So let's draw ourselves an origin, and let's use our line batch. And I'm going to stick this in some brackets so we can turn on and off and stuff later. If line batch dot arrow, and let's go vector2 dot unit x, from negative unit x to vector2 dot unit. So this is pointing in that direction, and head size, I don't know, what did I use in my test code? I won't cheat. I used 4 and 2. Okay, 4f divided by zoom and 2f divided by zoom. Color equals red, I think we're using for x. And then we can do the same thing for y. Now, if we run this, we should see up in the top corner our dinky little axes. And as you can see, we have to zoom right in on them, and they change size. So what we might do is we might just scale them up by like, I don't know, 20f divided by zoom, just so that they're that's a bit more sensible. And let's make the y-axis green just for congruency with, I don't know, a lot of 3D packages and stuff. So these are our axes, and we can zoom around, and they're there, and we can still draw shapes and stuff. So that's pretty straightforward. Now those are our x and y axes. What we want is some arbitrary axis that we're going to test against. So let's copy one of these suckers, and what we want is an arbitrary axis, and we can get an arbitrary axis fairly easy just by following the mouse cursor, because we've already got world mouse position. So why don't we just use that? So from the origin, vector2 dot 0, so unit x is obviously 1 unit long, so vector2 dot normalize. Actually, let's call it axis equals vector2 dot normalize world mouse position. So does this code that I've just slapped together very quickly make sense to you?
Normalizing the mouse world position.
I think it'll make a lot of sense once we run this code. So
yeah, I'm just trying to think in my mind what I was actually going to do, but hold on a second. Just give me a second to catch up. Or F2 up. Okay.
Cool. So this should make a lot of sense of what we've just done.
Whee.
So we're just following the mouse position.
Right. Well, yeah. when you normalizing the mouse position, and then you're drawing it from the origin to the normalized. Yeah, okay, sure, I get it.
So in a sense, what we've done, we've basically done world mouse position, not that one, but this one, world mouse position minus, minus vector 2.0, minus the origin. And obviously we can just elide the minus 0 because we're subtracting it. So that's how we turn that into like a relative direction and length from an absolute position. So the world, if you're conceptualizing it, the mouse position is an absolute position. Then we get a relative position by subtracting it from the origin, which is still exactly the same thing. And then we normalize it to get this thing. And as you can see, it's a normal because if we spin it around a bunch, this looks a lot like our unit circle diagram. We just got some arbitrary thing here. So what we're going to do, just to make the picture even prettier, is line batch dot line time, and we're going to go negative axis times, I don't know, 500f divided by zoom, and axis times 500f divided by zoom. Thickness is, say, 2f, and color is color dot white times 0.2f. So I'm just going to slap that in there. And the reason for this is it's going to make our diagram look even more like the diagram we were drawing by hand. And hopefully it should be fairly obvious what's going to happen here, but I'll let you run it and see what it does. So we have an axis, and hopefully this looks fairly consistent with that diagram. It's like, okay, we have a shape. What happens if we project onto that axis? So what I'm going to do, what did I do? I missed the zoom. And this is a bit short, so I'll just extend it a bit. But you get the general idea. Mm-hmm. So now we have this. That's all the pretty stuff done. Now what we want to do is reproduce this diagram. And to make things easy, we'll start with the circle, because the circle is really simple. If we have the center of the circle here, we want to project it onto there. So we'll go in circle mode for now. We can worry about the corners later, because that's just extra maths we don't need at the moment. So what we want is for each. That's right. We can't for each now because we've got a thing. But for all of our circles, let's copy down our circle thing here. We don't want to draw a circle because we already have that. What we want to do is draw this pink line there. And so that line batch dot line. So we know that it's going to start at the circle. So circles, you've got it. Yeah. So circle dot position to question mark. Thickness 2f by zoom, and color dot white will do for now. I don't know, times 0.7. So all we need to do now is just write our little projection thing in there. So this is one of those classic times where I'm like, all right, your turn to code.
Is it one of those classic times? Okay.
I'll just put this right here. This is this is our dot product. This is our C, length of C is this B cosine thing, and basically is A, this. So all you have to do is write that. And in fact, I'll even give you a hand. In vector 2, there's a static there's a static method that is dot.
Hold on. Guess this is not a thing anymore. Because, well, it's the length of b cosine theta, but maybe but we're doing that because that is what a dot product is. So the first one's got to be that, and then the second one. What's the second vector? The second vector is going to be the line, the axis line, which is it's just axis.
Yep, that looks pretty good to me. That looks like that one.
Yeah, but this is just a float, unfortunately, with this dot product thing.
So I mean, that's a good start. So we've got, all we have to do now is draw it, and so
now we have to extend it. We need to scale the axis by the.
That looks pretty good to me. Let me catch up, but go ahead and run that if you like.
Right, because we shrunk it, and then now we're going to extend it back. I am a genius.
Hey, it's working. Axis. Axis times dot product. And so what's really fun with this one is if you make a whole bunch of circles, you can see how this works. So now I have a bit of a visualization of basically what the projection operation does. So does looking at it like this sort of make even a little bit more sense?
Yeah, I mean, it seems like we did all that work, but finding like the length of b cosine theta, knowing that that's the dot product, that's what saves you, because then it's just a call to get it, and then the axis is whatever you want it to be. In this case, it's what we're drawing. So yeah, I mean, it's really nice when you can see it. I don't know, it makes a lot of sense. The projection thing is it's just getting to the part where you can like eyeball that and go, oh, right, that's the dot product, which is the same as the length of this vector with the cosine of theta, which is the same as projecting this down to an arbitrary axis from a given position.
Now what
yeah, I mean, it's hard, but it's
well we did cheat a little bit by using this dot product. Let's go in now and let's have a quick look at what the code for this is, because it's probably worth looking at. So the dot product of two vectors is this one,
right? X squared ax.
Well, no, it's not x squared. So value 1, value 2.
Sorry, it's ax.
Yep.
Yeah, right.
So
right.
that's,
oh yeah.
That
AX,
is
a1x, a2x.
Well, what happened there?
Ax bx. Whoa, cool.
Yeah. So there we go. Okay,
yeah, it's literally what you have there. Yeah, value 1 is a and value 2 is b. Yeah.
Yep. So
it's nice. It's nice to use F and A, because you can just get the sources right there.
Exactly. I don't think they have a projection, but I mean, it's not really that much more than a dot product anyway. Okay.
You want to do the rectangles?
Sure.
We might have time for that.
If you're keen to do rectangles, okay, so the rectangles look really good. The rectangles make this make even more sense. So let's copy down the rectangle thing, and
first thing I want to do is can I make this an arrowhead instead?
Sure.
You just have to slap a 4F zoom in that.
So if I yeah, okay, you still go. I mean, we can.
No.
Yep. And we can still run that, and yeah, we get a nice arrow. That's quite visually pleasing. So what I've done is I copied down exactly what you're copying now, but I can save us some time because we've already written this method, or part of this method, and that is the method that we're using to draw the rectangles calculates what the corners are. So I can just grab this.
Right. Oops, where am I? Lost. Oh, yeah, here we go. Blech.
So I'll let you do the honors of finishing this off, but it's pretty straightforward.
Okay, I thought we had to do a bunch of complicated stuff. Oh, that's separation against the corners. We're not doing that today.
We'll look into that tomorrow because we're going to have to convert all of our stuff over to doing this projection properly because we want our code to be. We want to get rid of sort of the sort of hacky ways we were doing it.
Well, wait a minute here. No, I don't want that. I want TL. Oh, this will be a pain. Maybe I'll just inline this back. From that point to the projecting it back onto the axis, yeah, I don't know. That looks fine to me.
Let's
Let's
give
see
it a
what
go.
I broke. Fun times. But I don't think
Almost.
that's right.
You've
Oh, I just screwed up one of
yeah,
the
just
points.
last
Yeah.
one.
Typo. TER, BR, BR. Yeah. That's cool.
So, and this should obviously look an awful lot like our diagram from up here.
Yep.
And so hopefully you can see now it's like, okay, here's an axis where they're separated, these two here. So obviously they're not colliding. Whereas if we were testing, say, that axis, there's two sections overlapping. Well, we might probably next time draw that in before we go too gung-ho on the actual separation part, because we'll need that. And then you can imagine, like, if we have two that actually are overlapped, there's no point as we rotate our axis around where they don't overlap. So that sort of gives you a taste for how the separating axis theorem will eventually work.
Yeah, I mean, I can see the value in, creating a visual tests game type project where, you would draw where everything is overlapping and switch boxes to green and red when they're, that kind of thing. But, which is kind of what we're doing now.
Yep, exactly. And, yeah, so you can see one interesting thing that happens, and this is why we're kind of fudging it a little bit, and that is you can see on the x-axis that this axis is shared. They all I can't move my mouse without ruining the diagram, but they all hit the same points. And if we do that on the y-axis, they all hit the same points. And obviously the reason for that is that they share, the x-axis and the y-axis that we were using that to sort of shortcut this process. So you can imagine if they were rotated or something, we'd have to test more axes, and then you've got an axis like this where they're not sharing points at all. And so we have to test, instead of 2 axes, we have to test like 4 axes for these shapes.
Right. It's kind of like just visual proof that you can't get away with that cheating we've been doing with this shared axis, because that's only one condition out of
exactly
infinite number of conditions.
Exactly. And I mean, probably, I'll leave it to your imagination. Like we could write the rotation code to make that rotate for one of them and see how that works, but we'll save that for another time. Okay, let's call it a day. Where's Hangouts? There's Hangouts. No, not Hangouts, OBS. All right, goodbye everyone.